Hi everybody, this is lecture number 4 and the title is Middlebrook's feedback theorem. This is very useful. Okay, all the ET are useful. Okay, so we covered two variations. First ET, suitable for the load impedance, load subsystem, and the alternative ET or second ET, suitable for the source coupled converter. Okay, so another variation of ET is this one, but this one is more general. Okay, so Dr. Middlebrook coined the term feedback theorem. This is very useful theorem. Okay, and this is the tool, an instrumental tool ideally suited for the system, feedback system analysis. Okay. Let me say one thing. In the electronics 2, you learned feedback amplifier. Okay. At there, you use some strange table, and the approach was you assume there was no feedback, and later on bring back feedback and divide something and something. Okay. That is maybe 95% correct. But 5% that is incorrect, not correct. Okay, so that is kind of fake for the undergraduate student. Okay, so that might be okay for the undergraduate student, but theoretically, you can find the counter example which negate the result of the table. Okay, so it is something similar to the fake, not completely fake. Okay. I taught the electronics for 20 more years, about 30 years, and I was using that table. But every time I explained to my student, this might be true for limited case, and we can make many counter examples for that, but this formula, this form is good for the undergraduate student. Okay. For the exact circuit analysis, that is not correct. You cannot apply that. Okay. And this one is the general tool. Okay. So this provides the exact, very exact expression for any feedback system. So practically most system has the feedback control now. Okay. So this is the formula for the people want to see the exact expression of some less exact expression, right? Something like that. Let me explain this. So there is Middlebrook's feedback theorem. So consider this. This is also two-port network. Okay, two-port. So this is input 1, input 2, output 1, output 2, but there is a feedback. Okay. This is the feedback structure. Okay, so among two outputs, only one is fed back to create this second input signal. So this is the general situation, very general situation. Okay, and this is the simplified notation. Okay, in the past I was using this to meaning this, but I found that the audience, they don't understand. Okay, so I did draw this, and now everything is clear. What I intended to consider as this one, but this is very complicated. It looks complicated, so I'm using this. Okay, but inside of this, you have this connection, right? Okay, so this is called two-port feedback controlled system. So this is a two-port network, and one output is fed back as the second input. This is the general structure for most the feedback system, right? And this is called, Dr. Middlebrook called two-port feedback controlled system. Then this is the equation. This is the feedback, the equation of feedback theorem. So for my proof is provided in chapter 9 of my book, my text. Okay, if you are interested in, you go to the book and read this part, but you don't need that actually. I found the easier way of proving this, so I'll explain that soon. Okay, So this is the equation. Looks complicated. Okay, but this one is much easier. This is 100% accurate. So we have terms here. Tm is loop gain. Okay, and we have H infinity. We have H0. Okay, and AS here is feedback gain. Feedback gain. Maybe the voltage feedback compensation for our converter case. And this AS is this one. So from the output of feedback, this is the feedback signal, goes to the directly output through this AS. Okay, so this is called forward term. Forward term. Okay, so it goes to the feedback signal and it goes to the other output with some gain. Okay, so it goes to this both way, but we are interested in this more. So it goes this through this. Okay, so that is the forward gain, and this -1 represent negative feedback. Most feedback is negative feedback unless you are making oscillator, right? So other oscillator, except for the oscillator, all the feedback should be negative feedback. So this minus sign indicate negative feedback, and this is the input to output from first input to the first output, not this one, not this one, this one, particularly this one, and the transfer gain from this input to this output is given by this Tm is multiplication of this, there is a loop, okay, loop. So it is negative number because there is a minus sign. So we add an additional minus to avoid the negative sign here. Okay, so this is a loop gain Tm, okay, but we have this additional minus in front, right? So this one becomes positive quantity, this loop gain, right? And H infinity is the transfer gain from here to there with this AS becomes infinity, okay? So it is scary. You are it's not easy to dealing with the infinity. That is not true. Okay, infinity is the easiest one to deal with. So this is infinity. Gain is infinity, but this output should be some finite number for the proper operation of this. Then this becomes what? 0. Okay. So this is the transfer function, where this output, second output is nullified. Okay? So the concept of output null is coming again. So this is, initially it is derived from the ET. So we are using the concept of ET here. Okay? So H infinity is the transfer gain. Evaluate H of infinity. We are not using this. To have a finite number here, then this should be 0. Okay? This is the case of ideal OPM. Okay, for the DC regulation, we are using the similar condition. So this is called, this H infinity is called feedback signal nullified transfer gain. Okay, this is very easy, easiest one to evaluate actually. Okay, so because for the finite UI2 with A of infinity, then this input should be 0. Okay. Infinity times some number becomes a finite number. Some number is 0. The only number is 0. So you have this. Okay. And H0 is this AS is 0. This is what? Open loop. Okay. Open loop. Input output transfer function. Then this is the open. Then input output. This is the open. Then that is this A11. Okay. Let me explain the pictorial illumination of this. Okay, this is very similar to the ET, but little bit different from that. Okay, you have this feedback theorem equation here, and the Tm is loop gain here. Okay, because this is the where the feedback signal is taken, and this is the where feedback signal is entering. So we have loop gain here, but there is just some connections in between. We are not showing that. Okay, we have the previous detailed presentation of this circuit. Okay, So Tm is this one, and this H0 is transfer function from here to there with feedback open, and H infinity is transfer function from this one to that with this gain becomes infinity. Okay, then you forget about infinity. Then this is 0. This is nullified. Okay, feedback signal is nullified. That is the condition here. Okay, one extremely simple example. I made this example to explain this. Okay, so single loop feedback system case. Okay, so this is the single loop feedback case. Okay, so we only have one single input, one single output, and there is a feedback signal is coming in like this and going like this. Okay, they are not existing here. This one, this gray box are gone. Okay, then this is the feedback system. Okay, when you are learning this in the automatic control course, right? Okay, so this is one differentiation of that, and we apply feedback theorem to obtain the input to output gain from here to there. Okay, then this is the general equation. Okay, then this one, this is the open. Okay, so this is 0. Then this one is going like this. Okay, so the gain from here to there with feedback open is A12. A12. Okay, A12 is the gain, and H infinity is the gain transfer function with A being infinity. That is the same as this port becoming 0. Okay, so we are evaluating this. We are evaluating from here to there, but this one is 0. Okay, that means this H infinity is 0. So this whole term is gone. Then this is H0 divided by 1 plus Tm. H0 is this one. A12 divided by 1 plus Tm. Tm is loop gain. This is the equation you have learned from the automatic control course. Okay, this is the simplest possible example of feedback system. But in many cases, the output voltage, output taken place is different from the feedback point. That happens in the feedback amplifier. Okay, for the feedback amplifiers, there are 4 types of series, shunt, blah, blah, blah. 4 cases, okay? And 2 cases are, some case is this single feedback path, but many cases you have 2 outputs and the feedback is taken from the different point, okay? Then you should use this. People are trying to use this rule forever with some simplification. Okay, that was their mistake. Okay, so it won't work for some case. Okay, all right. This is the Mason's gain rule. I modified this. Here, UI1 is multiplied with this, and it goes to the output. Okay, this is the same thing. UI1 is here. This is multiplied this and divided by this. So they are cancelled. So this is the same as this path, and there is a feedback. Okay, so the gain from here to there is there's one single output and a single feedback loop, and the output is the feedback signal, and it is also output of transfer function. Then this is okay. Okay, so you are only applicable. You only apply this equation for this case. Okay, there are many other cases in the feedback amplifier case. Okay, so that is the reason why this feedback theorem is necessary. Okay, proof of this. Okay, this is the new proof. So I derive this, and here, so UI1, UI2, UO1, UO2. So there is a path. I'll explain one by one. So there are 2 input. So this input is multiplied. This A12 appearing here, and UI2 is applied to with AS appearing here. Okay. If this is plus 2 and this is minus 2, output is cancelled. That means what? There is the output feedback signal null condition. Right? So always this condition is existing. Okay. At UO2 null condition, this output of this and the output of this are the same in the magnitude and opposite in sign, then output is nullified. Feedback signal is nullified. Okay? There is no mystery about the output or feedback signal null condition. That is the real condition. Okay. This is the feedback theorem we went through. So Tm is a loop gain, and this A11 is open loop transfer gain for this case. If this loop is cut, then this is the only signal path. There is A11, and H infinity is input to output transfer function with this feedback signal nullified, or this A is being infinity. This one. So put number 1 here, put number 2 here. Okay, and this is the standard equation for two-port network. Okay, so this is a two-port network, and this UO2 null condition is this one. UO2 is 0, and UI2 is not 0. Okay, that occurs right in this condition, and with this you solve this. So ratio of this one is transfer gain. Okay, with this one 0 is this one. It's the same thing. Okay, there is the definition of H infinity. Okay, so you can solve this. You obtain this. This is the H infinity. Okay, so that is the result of the ET. Okay, and we apply the basis gain rule here. Okay, basis gain rule is true. Okay, that general form is verified using some matrix determinant theory. The proving is very difficult, but we all know that formula is correct, accurate. Okay, then maybe you forgot that. Okay, in the denominator 1 minus the loop existing in the system. So I used the purple color. Okay, this one, and the denominator feed forward gain from the input to output. Okay, there is a one feed forward gain which is A11, and this term is 1 minus del 1. Okay, this is the del 1. Okay, there is the same as this one, but there is no touch between this path and this loop. Okay, you remember Mason's gain, right? That is what gain says. Okay, and another forward path is here. Okay, another path is this one, A12, AS, A21 with negative sign here. Okay, so this is the equation of basis gain rule. Okay, here this is defined as loop gain. So loop gain is this one. Then AS is loop gain divided by AS. So you replace AS to this one. Their equation is this one. Okay, you just replace the AS with this one. That is this one, and you rearrange this. Then this is the form, final form. Okay, so we know this is the H0, and we know this is the H infinity here. Okay, then it transforms this the general form of feedback theorem. Input to output transfer gain is loop gain is appearing here, and this is the transfer gain with feedback open. This is a transfer gain with feedback gain infinity. Okay, two extremes. Okay, so this is proved. This feedback theorem is proved using the basis gain rule. Probably I need to prove the basis gain rule, but I assume that rule is okay. Okay, so that rule is verified a long time ago by this Mason guy, so I don't have to repeat that. All right. This one is important. I explained the feedback theorem to explain this. Okay. this is our converter, so our uncoupled converter, and you are interested in this input impedance, which is transfer function from here, input impedance. This is the input, this is output, right? So we need to evaluate this, okay? And so there is a two input. One input is here. This is UI1, and UI2 is this one, red one. Second row, red one. And there is a one output, UO1, okay, in the first row with this blue color. And the second output is this here, okay. There's one feedback loop, okay. But output of our interest is this one, not this one, okay. So output of transfer function is here, but feedback is taken other point, the other point, which is output of this converter, but our output is this one, not this one, okay. Right, this one. So I translate, okay, so this is the converter, so this voltage feedback compensation, output of that is this control voltage, and the control voltage coming in, and this is the control to output transfer function, and the loop gain is here, okay. So there is the same thing, but I used the format of the ET, so UI1, UI2, you have two input, one here, another one here. You have two output, one here, one there. So this is the same notation, So this general rule can be used. This feedback theorem is used. Okay. So in here, I defined the admittance of this. The reason for this is extremely important. The input of this is not this one, this one. Okay. Because this is the voltage source. As the input is coming from some voltage source. So this is the input, then this is output. Okay? With that dimension, this is input and this output, then this becomes what? Not impedance. Okay? Not impedance. Admittance. Okay? So this should be written in terms of admittance. This is the valid transfer function. Okay? So for that, we apply this. Okay? If you think about this a little bit, this remains the same. This remains the same. Only H infinity and H0 are changed to this, changed to this. Okay? This is obvious. H0 is with feedback open. So this is the open loop input impedance. And this is the output nullified input impedance. Because this guy becomes infinity. To have finite number here, then this should be 0. Okay? So with that condition, we defined as input impedance GI double prime, GI triple prime. Okay, so I wrote down that here, and the feedback signal nullified, this output nullified input impedance. Okay, because FB becomes infinity, this becomes infinity, then our voltage should be 0. Okay, otherwise there is some contradiction. Okay, and this is the feedback open input impedance. So open loop input impedance FB is being 0, and this is loop gain, and this is the graphical illustration of open nullified input impedance, and this is what? Open loop input impedance. This is the final punchline of everything. So we have this expression, okay, very, very complex, okay, but somehow we apply the asymptotic analysis to there. So TMU is the loop gain of uncoupled converter, and this is larger than 1, smaller than 1. Borderline is what? Loop gain, crossover frequency, omega C, okay. So with using the omega C as the borderline, we have two rather crude approximation. Okay, so when TMU is large, is larger than 1, maybe very, very larger than 1. Okay, but if it is larger than 1, we ignore this term. Okay, this is very large, then this becomes 0, then we ignore this. Okay, this green part is ignored. We assumed this is 0. Then this is very large. Then this becomes 1. Okay, this is L'Hopital's rule, something like that. So 1. Remaining is this one. So the loop before the frequencies of the loop gain crossover frequency, GIU, 1 over GIU becomes 1 over GI double prime. Okay? So this is the output nullified input impedance is valid of this frequency. And after that, where this is smaller than 1, maybe much smaller than 1, okay? Then with this, so this is smaller than 1, this becomes 0. This becomes 0, okay? This is smaller than 1, then this becomes 1. Then remaining is 1 divided by GI prime, okay? So you swap the numerator and the denominator, then you obtain this, okay? The input impedance of uncoupled converter is this one, GI double prime, and at low frequencies, and after the loop gain crossover frequency of uncoupled converter, it follows GI triple prime, which is open loop input impedance. Right? Okay? And you can prove this, later we'll prove this. This behaves as the minus R for long range of frequency. Okay? So that comes from this at low frequency. Okay? Let me explain this. This GI double prime is this black curve. So it is, you can prove this, you can derive this. It starts from this straight line of minus RIC, and it goes up like this. Okay? You evaluate this, and this is the GI triple prime, so GI triple prime. Okay? Then this approximation says, this asymptotic analysis says, at low frequency, it follows this one, this GI double prime. At high frequencies, it follows this one. In between, it will be like it. Okay? There is some dipping at this omega C or near the omega C frequency. Okay? We don't have exact analysis around here, but it really doesn't matter. At low frequency, it is this, and then later on, it follows this slope. This is determined by inductor in the output filter of your converter. Okay? So, in the beginning of this part, this lecture, I said that the input impedance of the converter, regulated converter, behaves as minus R up to the loop gain crossover frequency of converter. Okay? It really doesn't matter, coupled, uncoupled. They are the same. Okay? So this is the result. Okay? This is the final confirmation of this argument. Okay? This is the voltage mode control case. Okay? So as I said, this curve is very sensitive to the converter topology and the control method. This is boost converter with voltage mode control. So you have this. I'm just showing 3 curves. Okay? So then this GIU follows this GI double prime at low frequency. So it starts here, somewhere here, at very low frequency. It is minus R, and it goes like this, and it converges to this one, which is open loop input impedance. Okay? So for this case, there are this dipping is apparent, but for some other topology, or color mode control, this will be gone. So sometimes it looks like this. It depends on the control method and your compensation design. Okay? For your reference, I plot the loop gain of this one using the same data. So loop gain was here. Okay? Loop gain crossover frequency was here. So this peaking frequency is different from this. Okay? There is just some deviation, right? But exact analysis in this part is useless. Okay? That is just a waste of time. Knowing this is enough. As the final example, people is thinking this way. This is the input impedance of uncoupled converter, and this is what? this is open loop input impedance of uncoupled converter. Then closed loop input impedance is this one divided by 1 plus TMU loop gain. This is true for the single output feedback system, output of a system, and the point of feedback signal expression. They are the same. This is true, but this is different. Okay, output is there, feedback is there, but our output is somewhere here. Okay, then you should use this one. This formula, Middlebrook's formula, feedback theorem. So if you use this one, you believe this is true. Many people believe this is true, and this is plot. So this is GI triple prime is here, okay, and the GI triple is this, okay, and this loop gain. So loop gain is this much. So this is dropped by this much. So you are subtracting this value by this much. Then output impedance looks like this. Okay. After loop gain crossover frequency, it follows GI triple prime. I just showed this GI double prime for your reference. Maybe you forget about this. This is the wrong result. Okay. This is the case I was mentioning in feedback amplifier analysis. They are doing this. Okay, some case. So that is absolutely wrong, as shown here. Okay, this is verified experimentally and by simulation. This is correct equation to use for the input impedance analysis. Okay, so this approximation is rather crude. Okay. So we are assuming this is 0, okay? Maybe this is the 2, there is 1/3, but we are assuming that is 0. So there is some error, okay? Deviation in between. But exact analysis is unnecessary. You can simulate this, or you can ask ChatGPT to plot this, okay? That's not your job. This is the end of this topic 13. So we went through all the details about the ET, and I hope you find some application potential of ET. Okay. So there are two kinds of people. One is who knows ET, who does not know ET. Okay, join me. Okay. Some reference, okay. So, all right. Still, I have 1 minute. So, this is the paper. Our father, Dr. Middlebrook, he introduced the concept of null double injection and extra element theorem. Okay, this paper was published this year. Okay. But he used some result of this maybe 20, 30 years ago, earlier than this one. But, so he knows this, but he didn't publish it. Okay? And he didn't apply this theory to the converter analysis. Like me, he used this technique to evaluate the input impedance of converter, because the interaction between infilter and converter was very important in the past. Okay, and he proposed some method to avoid the instability, and I improved a lot, and I published the paper 1990, something like that. Okay, and many people published many variations, which are mostly stupid. And 4 years ago, I published another paper closing all the argument. I initiate the struggle, the fighting, and I closed the fighting. Okay, that is the conclusive paper about this issue. Okay, so maybe there is a chance to introduce that to you. Okay, all right, and this is this one, an extra element theorem. the hardest part of this paper is the length of this paper, 20 pages, something like that, and the notation is crazy. Okay, so they are considering all the possible cases. So one letter has 3 subscript and 3 superscript, dash, something like that. Okay, so don't try to read this. All right. And this is the book. This guy, Napoleon. So he introduced the proof of this one. He proved some strange way, and this is the mathematical proof. The Hendrik Baudet insinuate he didn't publish the paper, but if you read his text, he was referring that method. So this the Bache wrote one chapter of proving that. I spent some time to understand that. Okay, and this is some introductory paper, and this is the paper about the design, saying the design of uncoupled converter is practically same as design of resistive loaded converter. Okay, that is also important. Okay, the result is extremely simple. Okay, but good to know. Okay, otherwise you will wonder forever why we are assuming the resistive load all the time, and no load is actually purely resistive in real application. That kind of things. Right? Okay, so this is the end of topic 13, and next week we'll move to the topic 14, and we'll discuss the every details about load coupled converter, and at that time we will be repeating many of this in short form. Okay, so no more pain there if you admit the correctness of ET. Okay, all right. Okay. Just on time. Okay. All right. Thank you. We stop here.